It's Doug Littrell. It's June 2nd. I'm sitting in my living room. I've been doing some tests with my version of the Pithball electroscope. That's what I've got on the coffee table in front of me. Slide it over a little bit. It's kind of like a tree or something. There's a vase for flowers there. These plastic tubes are stuck into it. There are balls attached, objects attached to the ends of these. The string isn't responsive to electric charge, at least not visibly. So here's a couple of ohm meters. One's digital, one's analog. Let me explain my setup here. That's part of it. Here's a couple of conductors. You wouldn't maybe think of lead as a conductor. Here's some lead left over from my when I cast my 2 lead balls for my track experiment with the balls rolling down the lanes in the track. It's actually a conductor. So is this is just some aluminum foil. Of course, it's a conductor. A couple of these balls are painted with metallic paint, and I found out the metallic paint that I had at least had 2 brands, and neither one are conductors. Neither one will conduct electricity. When you put the ohm meter on there, there's no continuity. I've also got a magnet here, a horseshoe magnet that's on the end of this handle. That's used for picking things up that are metal. I actually bought this for an experiment, and then I put it on this. I had a different magnet on here originally. I used those magnets to do some tests when I first started to explore things in physics a little bit with magnets. That was like 10 years ago. And now I have this horseshoe magnet that I purchased, and I put it on this tool for picking things up that are metal, that are magnetic, ferromagnetic. I've got this cotton cloth here. It's a little bit of a rough version. It's actually a placemat, and I'm using that to build up charge, you might say, and this plastic tube. This plastic tube is 1-inch PVC. It's thin wall, and so I use this to rub it. Yesterday I was doing it 20 times when I was using it against these different balls to see which ones, how they would respond compared, like the hollow plastic ball compared to the hollow plastic ball that's painted with that metallic paint. Let me move the camera closer. At this close range, you won't be able to see everything on the table now, and you won't be able to see, oh, it almost cuts my head off, but let me go ahead and explain some more, and this will be a little better in some ways because it's closer. Here's that analog ohm meter. May not be able to see this, but when you hook it up to the metallic paint, nothing happens. When you do that with the lead, even though we don't think of lead as being a good conductor, I'm having a little bit of trouble with this one. There it goes. Yeah, pegs the needle. The needle pegs out when you just put both probes on the surface of the lead, and then when you drop one off, see the needle goes down. You probably didn't see that, it's too far away. The same thing happens with of course, with the aluminum foil. I'm touching it now, and it pegs. The needle pegs out. With the digital meter, it shows the number 1 when it's set on ohms, and then when it goes to 0, there's continuity, it goes from 1 to 0, and you could get value readings if you had a difference in resistance and between materials. When rubbing this wand, now so let's say yesterday I was rubbing it 20 times. And then I was setting it on this table, and you can see how much that plastic ball is attracted to it. It will move over some 4 inches from where it would hang straight. Now I did that yesterday, and I timed it. I had it attached and moved over about 4 inches, and it fell away after about 13 minutes. And it was still attracted, but not enough to hold it 4 inches. I did this yesterday with the hollow plastic ball that's painted, and it attached and moved over some 4 inches, and it stayed there for an hour. I timed it watched the clock from 12:07 p.m. to 1:07 p.m. and then the ball, I was in the room when it fell away, and I saw it fall away and swing. I tried the same thing with the metallic painted rubber ball. It's not hollow. These two are the same, only this one's painted with that metallic paint that doesn't conduct electricity. Anyway, it would pull it over about an inch is what it ended up pulling it over when I had this on this table, and then everything was still, and it stayed put. Get this, for 3.5 hours it was connected, had moved it over about an inch, and it did not fall away. It took over 3.5 hours. Now, this is not the case with the unpainted rubber ball. The same diameter, same density, and it's rubber. It's attracted, but not as much. And I couldn't get it really to attach and pull over significantly like it is doing now. It responds a little bit, but not much. So there's something in the metallic paint, and it's not because it's a conductor. The paint is not a conductor, but there's something about the metallic paint that makes quite a bit of difference in how long this ball holds next to the wand compared to this, an hour compared to 13 minutes, 3.5 hours compared to almost nothing. Almost nothing. And also, when these balls fell away that were 4 inches pulled over from where they would hang without the attraction, they were still attracted at a close range after the time had elapsed. Now, I might be discharging this to some extent because my hands against it and my feet on the floor, perhaps. But let's see here. This is what I made today. This on this thread instead of this nylon string, which is really good for this. This nylon string seems to be very good because it doesn't interact. Now the thread, I was surprised, seems to react. It's not. It doesn't react as since this paint was not an electrical conductor, I was trying to reproduce what some videos on YouTube have shown with the pith ball experiment. I was trying to show how you could get attraction and then repel with the object on this that's dangling. The way I did that, I got a small styrofoam bead, and of course, with it having less mass, it responds more because it doesn't have to move the mass against its attraction to the earth, which is the problem with all of these. The gravity, you're competing with gravity when you're doing this. Gravity wants to hold it straight down. But this is a styrofoam bead with some of that aluminum foil wrapped around it, and then I took a sewing needle and put through it so I could get the thread through, and then tied it on here, and so you can see that it's attracted. But it's all, you can also get repel out of it. See, there it's repelling. It seems to be like one of the video makers said that one side attracts, and then another side of the aluminum foil, or if you had paint that conducted electricity, the other side of it repels. I'm not getting that right now. Of course, this is almost needs to be rubbed again. This styrofoam bead with this foil on it is very responsive. You don't have to rub this very many times. Look at that. I don't know if you can see it or not. Look at the repel that thing has now. Look at that repel. Is that showing up? It's raising it. Now, if you go down below it or on the other side, look, now it's attracted. So one side is attracted. Of course, this thread is also it's reactive in this experiment. So it's not as good as the nylon, apparently. There it is. There's a side that's attracted. There it's attracted again. And then go up high with it here, and now it's repelled. Now it must be turning, and then it can attract. So there's something going on with the sides. Something with the sides that causes repel and attraction. Now, I'm not going to interpret all of this today and tell you how my atom model solves everything today. That's for another 1 or 2 or however many videos it takes. I'll be working on that. But I will show you something with this magnet, and this is a copper ring. The copper ring is not attracted to this magnet. Now with this horseshoe magnet, what you have some of the universe's smallest digits of matter which are photons. There's a couple of variations of those that have a certain charge, they're middle charged, and those are the electric photons that are circulating in and out of this magnet right now. They are making a circuit through it. They enter its north pole, they exit its south pole. We don't know which is the south and north pole at this time. There would be a way to find that out, but I believe, but I haven't determined that. But those photons are flowing in one of these and out the other. And as they do, they move across, and if they have mass, see, then they would kinetically impact. This is what magnetic fields do all of the time, and they use them for, is to kinetically interact and determine the mass of objects, such as in mass spectrometers. And they use magnetic fields in so many different ways. The Earth's magnetic field helps protect us from harmful material headed toward the Earth. These reactions out here in the environment, in space, but also in the atmosphere here, this is a kinetic. These have mass, and it's a kinetic interaction. I'm going to show you. This copper ring is not attracted to this magnet. Now, if it were iron or steel, it would jump right into it. I'm not going to go into explaining why copper isn't attracted and steel and iron are. But look at this. You can, because those are flowing in and out. This is not negatively charged and this is positive. These two poles are not negatively and positively charged. That's not what's going on with magnets at all. These particles are flowing in one pole and out the other, and circulating around and coming back in. And because these photons have mass, they collide with the copper ring. I'm not touching the copper ring, but I'm moving it because those photons are colliding into it right now. Okay, that's the only interpretive content that I'm going to have in this particular video. See it moving back and forth. Okay, I've moved the camera a little closer. There's my cat. She came in. She's in the video now. Okay. If I tilt the camera, I'll get most of my head in, and I want to get it closer so that this is the bead of interest. Let's see. Let's get it moved over here. Well, I have to pull it back a little bit. This is the bead of interest right here, the styrofoam bead with the aluminum foil over it. I've trimmed off the end. The thread was coming through, and I thought that might be a little bit of a problem with when I'm trying to demonstrate the wands, how that they have more intensity and then less intensity in the reaction. I used this one part of the time yesterday, and it's a mini blind rod, you know, for opening and closing. It's still the bead reacts to it. Of course, it didn't have this bead yesterday. All these others are balls, except for so I'm just going to call this a bead. Or I say bead, I'm talking about it. It'll attach to it, looks like. Yeah, there it's attaching, it's moving over. So it's interesting that there's still something that's changed. in this rod. Now, I've taken this rod outside. Now look at the other end here for a minute. And it's also interesting that the other end, it's not responding to the other end. That's it. This was the end I was rubbing yesterday when I was using this, and it still responds to that end, but not the other end. I'm not seeing anything with the other end. It's interesting too because I've taken this outside today and dipped it in water, a barrel of water, splashed water down the concrete on the ground, touched it into the water, held it there, and it didn't change anything. It still wants to be attracted a little bit, and it it's funny. It's not wanting to repel now. It wants to attract on one side. Seems to be dissipating. Yeah, there's a little bit of seems to be dissipating now. Just by that interaction, help to dissipate. But what I wanted to show is mainly has to do with this larger wand. You get more of a reaction out of the larger wand. Now it's attracting now to this end, and I haven't rubbed this for quite a while. Now, before I filmed this, I did the same thing. I had to do a retake. I was getting this wand to make it repel, and it wouldn't attract for quite a good period there. Now it wants to attract and not repel. So that's a clue too. Notice this other end, like the other wand, this other end that hasn't been rubbed is not very reactive. It's very mild. Not much going on. Okay, so there's a difference in the ends. And that's what I was wanting to show. Now when you say rub this one end 5 or 6 times, maybe 7 times. Okay, now it's highly attracted. It's repelling, it's highly repelled. There it's attracted now. It's pulling, almost pulling the thread out straight. The thread is a little bit rippled, you might call it. So it's working. Now the other end that I didn't rub, let's check it. It's reactive enough to attach now. There's a little repel right there. A little bit. There's some repel. Oh. There it's attached. It fell, but it's it's a lot milder. The effect is a lot milder in the end that wasn't rubbed. Now some of it is bled through from the rubbed in, but this one's still, this is bleeding off, dissipating now. The effect is dissipating now, but it's still significant. You know, it's not nearly as strong as it was when it was pushing the bead clear up here when it was repelling it, or, you know, when it attached to it, it would lift it way high. So it's dissipating. And I just wanted to show that because when I started explaining how this works with the atoms involved and the shells, what I'm going to say are radio shells, you know, all of these observations are natural ones, and they're real observations, and they need to be explained, and I'm going to try to do that.